Hello, this is Jack Jackson again, and we are continuing to look at matrix representation of isometries. In the previous sections, we've introduced two different ways of representing transformations with matrices. One uses certain 3 by 3 matrices with multiplication of matrices producing a group structure, and the other uses certain 2 by 2 matrices producing a vector space structure. However, we haven't yet identified, or at least not very often, which matrices correspond to which transformations. And we're going to do that in this section here. There's a table below that gives the transformation matrices that can be applied to perform some standard transformation. The exact form of the matrices for the identity transformation, translations, rotations, reflections, and glide reflections are given, all the basic types of isometries, and some specific reflections and rotations are given as well. Both 2-column and 3-column versions of the matrices will be given. In the 2-column version, matrix addition and multiplication are both utilized, along with scalar multiplication, viewing isometries as a vector space. In the 3-column version, only matrix multiplication is utilized, interpreting these matrix versions of the isometries as forming a group, just as we viewed isometries with composition as a group. In either case, transformations are written so that the transformation matrix is always placed on the left in the computation. You put the point matrix on the right, and you put the transformation matrix on the left, and the resulting product is the image of that. When the product of two transformation matrices are done, we perform the one on the right first, and then the one on the left. This is consistent with the way we read transformations right to left as we did composition of functions. But notice that we are applying these matrices from the left. Again, this is consistent with the way you're used to writing compositions of functions, and it's how we proceeded throughout this text. However, many people, I just want to point out, use a notation that starts with the matrix of preimages on the left, and then apply the transformations on the right, working left to right, like the order we read in European languages. In this approach, the points are given as row vectors, and the transformation matrices then are the transposes of the corresponding matrices in the notes that I've given below. Actually, I prefer it that way. Group theorists typically use this right-handed notation, which is consistent with the way we read English, left to right. One might be so bold as to say that only these people are in their right minds, pun intended. But alas, I am a group theorist by training, am outnumbered by most geometry text, your linear algebra text, and your previous experience in calculus and pre-calculus, so we will use left multiplication throughout in this course. Recall that isometries preserve distance, angle measure, betweenness, area, and congruence of geometric figures. So in the table below, P stands for a pre-image matrix, and the result of the operation in the table is its image matrix. In the case where additions are used, in the left column, P is a 2 by 1 matrix for a single point. If P is a matrix for endpoint, then we adjust it by the matrix HK to have n columns that are all the same, all HKs. Notice that for the identity transformation, rotations, and reflections, the 2 by 2 matrix version only uses matrix multiplication, and the 2 by 2 transformation matrix is the same as the 4 entries in the upper left corner of the 3 by 3 version, and in this case, where the no translation is involved, the last column of the 3 by 3 transformation matrix is just 0, 0, 1 like that. Of course, the bottom row is always 0, 0, 1 going across from left to right on the bottom column on any transformation matrix. Translations and glide reflections involve at least one step using matrix addition in the 2 by 2 version, and they involve multiplying by matrices with a non-zero entry in the last part, so this is not necessarily 0, 0, 1, it's something, something, 1 with one of these not being 0 in the last column when using the 3 by 3 versions. Okay, so let's get into the details. So what's the identity transformation? Well, you multiply by the identity matrix. Well, the 2 by 2 identity matrix is like this, 1, 0, 0, 1, and the 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. In both cases, you have 1s on the diagonal and major diagonal and 0s everywhere else. To do a translation using the 2-column matrix, you take the point and you just add h to the x coordinate and k to the y. So the first row and the first column, and then the second row, first column, you add k. Notice what we have here. We have the identity matrix in the upper left column, but then we have this same matrix HK in the last part here. And if you multiply that by this, that's going to give you the translation. We're going to verify some of these 3x3 versions a little bit later as we go along here. Here's some specific reflections. If you multiply by the matrix 1, 0, 0, negative 1, that's going to reflect over the x-axis. That will end up changing the sign on y, but leave the x alone. And in this version, it's the same thing, 1, 0, 0, 1 up here in the upper left corner, with 0, 0, 1 down the last column, and of course 0, 0, 1 always on the last row. Reflection about the y-axis takes your identity matrix and puts a -1 on the upper left-hand corner instead of the lower right-hand corner on the reflection about the x-axis. Notice if you do this, you will end up changing the sign on x and leaving y alone, which is what reflects about the y-axis. Once again, this upper corner is the same over here for the 3-column version. If you want to reflect about the line y equals x, you use the matrix 0, 1, 1, 0. Again, it's 0, 1, 1, 0 here in the upper left corner with the 0, 0, 1 down the last column there. Now, a reflection in general about a non-vertical line with slope m, y equals mx plus b, is a little more complicated. Okay, one way you can get that is take 0b and add that to, well, let's start here. Start with the point matrix, multiply by multiply by 0, negative b. Then multiply by this matrix here, cosine of the opposite of the inverse tangent of slope. This is the opposite of the sine of inverse tangent of the slope, and so forth. Then multiply by 1, 0, 0, negative 1, and then add 0b. So what we're really doing is, actually I think this one's supposed to be a plus. What we're doing is translating to up or down by b so that the line is essentially going through the origin. Then we rotate through the origin, and then we translate back up. If you work all that out for a 3x3 version, this is the formula here in terms of the slope and the y-intercept, y-coordinate y-intercept. So there's some b's over here in this last part, and then the rest involves m's. Notice we have a common denominator of m squared plus 1 everywhere, at least for the first 2 rows. I'll have to go over why this works a little bit later. Okay, it's a little more complicated formula, but there it is. If you're reflecting about a vertical line, you can multiply by negative 1, 0, 0, 1, and then add 2h over 0, which is essentially does the same thing here. If you look, see the negative 1, 0, 0, 1, that 4 entries are the upper left corner, and the translation here is your 2h and your 0 here. Okay, and I'm not going to worry so much about the 2-column version, but in the 3-column version, we will verify that all these things work. In general, a rotation through the origin, about the origin through an angle of theta, is given by this 2x2 matrix, cosine theta, negative sine theta, cosine theta. And that's kind of what we were using right here, where the theta is the opposite of the inverse tangent of the slope. Here we are we have the same thing right here with 0, 0, 1 on the last column. So if we put in some specific things, for example, if we put in say pi, rotation about the origin, okay, cosine of pi is negative 1, sine of pi is 0, sine of pi is 0, cosine of pi is negative 1. And so if you multiply this by a point, notice it will do exactly what it's supposed to do, change the sign on both x and y. And so this one turns out to be the same thing here with this here. If you rotate by an angle of pi over 2, again, you can use this general version here, substitute in pi over 2, and see that you get this here. And once again, double check that this works out to be what we've seen before. And once again, these 4 entries are the same as the 4 entries in the upper left corner here. If you want to rotate about a point HK, the way you can do that is take the point, translate by minus h minus k, which basically translates it to the origin, rotate around the origin by theta, and then translate it back up by hk. And so that process will give you a rotation about a point, any point through an angle theta. And if you do that, well, we can get this matrix by basically multiplying these matrices, right? So you multiply by a matrix like this with minus h and minus k on the right. Okay, then the second one on the one to the left of that would be this matrix right here, this one right here, which rotates about the origin through angle theta. And then finally you're multiplied back by this one right here, which is going to translate you HK back. And if you multiply those 3 matrices out, this is the matrix that you end up with. Yeah, I didn't even bother working out the glide reflections over here on the 2 by 2, but I do have them worked out here about a mirror line y equals mx plus b and a parallel vector hk. Notice that k over h is the slope of that mirror parallel line. And so how did I get that? Well, basically I just multiplied the 2 matrices, one that where we already knew. Let's see, what is it? We first do the translation. So I took this matrix here, wrote it first on the right, and then on the left wrote this one here, replacing m by k over h. Multiplied that out, saw what I got, and I ended up with this thing here. To be honest, I cheated a little bit. I used some technology to help me with those multiplications. Could have done it by hand, but just easier with some technology. And then this one, that's not going to work if you have a vertical line because it's not a y equals mx plus b. So line is x equals h and a parallel vector 0k. And I worked out what that would be, and there it is there. So this gives you a really good reference then. You might just screenshot that and that, and that will give you a reference there, okay? So again, notice that the 3-row matrix versions of these transformations produces a group isomorphism between isometries with composition as the operation and the set of certain matrices with matrix multiplication as the operation, and which maps the indicated geometric transformation under composition to the corresponding 3-row matrix with non-zero determinants under the left matrix multiplication. So from here on, we'll use the 3 by 3 matrix versions of the transformations. This version is more directly consistent with transformations since we only use one operations, matrix multiplication, corresponding to the one operation for transformations, composition of functions. So let's verify some of the matrix representations given in the table above. First, let's do this one. Let me see. I'll leave this as a task first. So verify that this actually does, in fact, give you a translation of the point x, y by the vector hk. So just do the multiplication out yourself. So I'd actually like you to do that now. Press pause and work that out. Okay, well, hopefully you did that, and now you're back and have worked this out, but here's the details of this. So notice that when we take the first row here, 10h by x, y, 1, we get 1 times x plus 0 times y plus h times 1. Well, 1 times x is x. The 0 times y goes away, and we have h times 1 is h, and so we get x plus h. Similarly, if we take the second row times this, we get 0 times x plus 1 times y plus k times 1 is y plus k. And the thing you're always going to get every single time, so you don't even really have to do this when you can just write 1 at the bottom, is because if you have 0 times x, 0 times y, and 1 times 1 and add those together, you always get 1. So you don't even have to think about that one. You can just write the 1 at the bottom. Okay, well, notice what happens. This says that the ordered pair xy, right, is mapped to the ordered pair x plus h, y plus k, which means is exactly what we mean when we translate by the vector hk. So that's the right one. Okay, so I'm going to actually leave these as exercises for my students and for you as well. A couple of these you can verify. So verify that if you multiply this matrix by this, you're going to get output that is the image of this point xy about the origin rotated through an angle of theta. So what you're going to need to do is look back. If you have my text, you can look back to an earlier section where we derived the correct formula for rotation by an angle and see that it works out the same. Or you're going to have to look back in the playlist and find the video where we did that and jot down that formula, and you'll see that it works out. Okay. And this exercise, compute the result of the use this result, right, to verify that multiplying the general point xy1 on the left by this results in a rotation about the origin of an angle negative pi over 2. Again, look back at what we had done earlier about what you need to do to the points xy to get x prime y prime when you rotate by negative pi over 2. We did that in an earlier video. Multiply this out and make sure those results match. So check those. Okay. Verify that this is appropriate thing for a reflection about the line y equals x. Remember, x should be sent to y should be sent to x. Make sure that this actually does that. Again, in each case, you're taking these matrices and just multiplying them from the left side to onto or by the xy1, which is on the right side. And then here's another one. Verify that this is appropriate for a reflection about the x-axis. What should happen here is it should change the sign on y and leave x alone. Okay, so I'm going to let you verify those. Now, here's a reflection matrix. This one's a little more complicated, but it results in the reflection over the line y equals mx plus b. Now, how did I come up with that? Well, we're going to use matrices to translate the line up or down to go through the origin, rotate it to the x-axis, reflect over the x-axis, rotate back, and then translate back up or down. So specifically, to obtain the reflection of this y over the line y equals mx plus b, we first translate it vertically by the vector 0, negative b. So now we know, now our line is going through the origin. Then we rotate by an angle minus arctangent of m. That'll rotate it so the angle that the line now becomes the x-axis. Okay, then what do we go to do? We rotate it, we reflect over the x-axis, then we rotate it back, and then we translate it back. So a couple of things here I want you to notice is that when you have this angle theta, the slope of this line is how much you go up or down when you go to the right one. So it's this red signed length. And if it's going up from the up and to the right, up as you go to the right, that's a positive slope. If it goes down as you go to the right, that's a negative slope. So this is the slope here. Well, also notice that if you take that is right triangle right there, if you take opposite over adjacent, that's the tangent of that theta. Okay, so tangent of theta is actually the slope of that line. Okay, so that's an important observation. So theta, the angle that it makes with the horizontal, at least one of the possibilities for say that theta, the easiest one, is the arctangent of m. So cosine of the arctangent of m, what is that? Well, look at this picture. According to the Pythagorean theorem, this side here is the square root of m squared plus 1 squared, or the square root of m squared plus 1. Well, the cosine of this angle would be adjacent over hypotenuse. That's 1 over the square root of m squared plus 1. And the sine of theta is opposite over hypotenuse, the hypotenuse being square root of m squared plus 1. So that's m over square root of m squared plus 1. So that gives us some nice reductions for those sines and cosines. Okay. So this particular theta, we'll be able to substitute these things in for cosine theta and sine theta in a bit when we need to. So here the details worked out. Okay, so notice this matrix on the far right is going to be a translation by the vector 0 minus b. That's going to shift your line up or down as needed so that it goes to the origin. This is a matrix for rotating by the angle minus theta. So that's going to take that and rotate. If this is, first of all, you shift it down 2, and then this angle theta is going in the positive direction. We rotate the opposite direction, minus theta, we'll turn it into the x-axis. And that's what I give him by that matrix. Then this matrix here is a matrix for reflecting over the x-axis. The next one, remember, notice we're reading right to left. The next one is rotating back by theta. So after we've reflected it, rotate it back by theta, and then move it back up or down by b so that we're back at the point we started. And this will work out so that you get the reflection that you want. Okay, and then it's just a matter of multiplying all of this stuff out. The only thing I did here is did cosine of minus theta. Cosine's an even function, so cosine of minus theta is cosine theta. Sine is odd, so that's minus the sine of theta. The two minuses cancel out here, but the minus goes away here. So now I have everything as just as a function of theta. Now I just start multiplying. Actually, before I start multiplying, I actually substitute in. Cosine theta was 1 over square root of m squared plus 1. So where we had a cosine theta there, and there, we have 1 over square root of m squared plus 1. And sine of theta, where we have that, is m over square root of m squared plus 1. Some cases there's a minus out front. Now we just go about multiplying these. It's associative, so I can kind of do it any order I want. What I ended up doing was grouping these two first. And there's the details of multiplying that out. And that becomes this matrix. And then multiplying these two out gives you this matrix. Now I'm just going to leave it right there for a second. You can pause that and look through the details if you want. I'm not going to verbally say every detail. Okay, now if you're back, hopefully you're okay with that. So then I multiplied these first two together and got this matrix. And now finally the more complicated one is multiply these two together. And there's some details. And we get the matrix that we're supposed to have. So you can work all that out by detail. And like I said earlier, I used a computer algebra system. In my next video, I'm going to show you how to use a TI Inspire CAS to do these matrix multiplications to make this some of this tedious matrix multiplication a whole lot easier. But I did it with the matrix with the TI Inspire CAS, or you could use some other program that multiplies these things in general with the computer algebra system. And I verified and made sure I got all the steps right, which I also did by hand here as well. Now, again, how can we be sure? I mean, I went through these steps. Hopefully it sort of makes sense why these steps might work. But how can we verify that this actually works? Well, let's do it directly. If we take a point A, which is xy, and compute its image x prime y prime by multiplying by this matrix. And then let's make sure that that it is a reflection over the line y equals mx plus b. So in other words, the midpoint of the line segment from A to A prime needs to go through the line y equals mx plus b. And the distance, well, we can do it another, that, and it also needs to be perpendicular, okay? And so we can compute the slope and show that the slope of the line from A to A prime has to be the right slope, which is the opposite of the reciprocal of the slope of the original line, and that'll make it perpendicular. So here's some details. So here's our matrix that we just came up with. If we multiply it by the point xy, the matrix for the point xy, that's this xy1, here are the details worked out. You got this first term times x plus this term times y plus this term times 1. That's the first one. That's y. X prime is that top number. And then y prime is this one. So what's the midpoint? We take x plus x prime divide by 2 for the x coordinate, y plus y prime divide by 2. So here we go. It's a lot of tedious symbols here, but it's a straightforward idea. You just take x plus this guy right here. There it is. Divide by 2. And you take y plus this one divide by 2. Now what we need to show is that this is on the line y equals mx plus b. I did a little bit of, we got fractions inside of fractions. So in both fractions here, I multiplied top and bottom by m squared plus 1. And we get that. I did some distributing here and here and combining like terms. And eventually it settles down to this one right here. Again, I will leave that right there for a second if you want to stop and verify the details. Okay, or you could use a computer algebra system to do it. But this works out. So now if you take this and multiply by m and add b, you get this. So if you take this x coordinate, multiply by m and add b, what do you get? Well, look at that. In the end, you get the y coordinate. So the midpoint is on the line y equals mx plus b. Okay. So the midpoint of that line segment connecting pre-image to image is, in fact, on the mirror line. So the mirror line is going to bisect that line segment connecting pre-image to image. Is it a perpendicular bisector? Well, let's look at the slopes. The slope of line A to A prime, okay, is y prime minus y over x prime minus x. Well, again, if we just pull our y prime and x prime formulas from up here and subtract y on the top, subtract x on the bottom from the x prime. So that's y prime minus y on the top, x prime minus x on the bottom. Now it's just a matter of doing some cleaning up here. Multiply top and bottom by m squared plus 1, get you to here. Distribute and combine like terms. And then we're able to factor out a 2 and cancel it with the 2 factored out the bottom. And then at the bottom we can factor out a minus m. And then this part's the same. And the dust settles, it's minus 1 over m. Hey, that's good news because that means that line, that slope, that line segment or the line containing those 2 points is perpendicular to the original line y equals mx plus b. All right, so it all works out. A lot of kind of gory details there with all the formulas, but the bottom line is it works, right? And we proved it works. So here are a couple exercises you can use. So there's our formula. So let's take a vector, let's take a vertex points 0, 0, 1, 1, and 2, 3 for a triangle reflected about the line y equals 2x minus 3. Now before we did these sort of things, synthetically, we would draw the graphs, we did reflections by, compass and straight edge constructions and so forth. But this one, we're going to use it analytically using the matrix. So just put in the, the appropriate m and b in this formula. Remember, the 2 is m, negative 3 is b. Get your matrix here with actual numbers. Multiply that by the appropriate point matrix and see what this turns out to be. And then I want you to check your work by going to GeoGebra and draw the triangle out and graph this line and reflect it and make sure that the points, the image points, are what you computed here. So the two things should agree. All right, and here's one more that I want to do as an exercise. Verify that the inverse of this matrix is this one. Okay, I've got this worked out using some techniques I don't want to bother getting into right now. I figured out what this matrix is. So how do you prove this? You would take this matrix here without the inverse and multiply it by this, with this one's on the left and this one on the right, and then do it again with this, the inverse matrix here on the right, left, and the original matrix without the inverse on the right. Do it both orders, and you should get the identity matrix both cases. So double check that and verify that is the appropriate thing for the inverse matrix. Okay, of course, for this to make sense, the AD minus BC has to not be 0. So certainly transformations will be that. Okay, and another thing that you might show is if this has a determinant 1 or negative 1, so does the inverse. In fact, yeah, if it has determinant 1 or negative 1, so does the inverse. Okay. All right. Next video, we're going to talk about how we can use some technology to make a lot of this stuff a little bit simpler.